All right, in our second question, we are trying to find stability for chair conformations. And normally the way we approach one of these problems is by finding the largest group, which is often a T-butyl group, making sure we put that substituent into an equatorial position, and then kind of filling in everything else around that. Well, in this case, that's not going to help us. And the reason that's not going to help us is that in this case, every substituent we have is a methyl group. And so what we'll be looking for here is how do we get as many of them equatorial as possible. And so let's draw the two possible conformations. So I'm going to choose this carbon as our starting point. And since that's down, I'm going to make that equatorial down here. Going around this way, the next position, equatorial up, or is up, so it has to be equatorial. Then we have another substituent is up, which makes it axial. The next substituent is also up, which makes it equatorial. And then the last two carbons have substituents in both directions. Now, this methyl group that I had started with, I could have instead put that as an axial position. If I do that, that means I would need it in a spot like this. And then we will have axial up, equatorial up, axial up, and then the last two carbons, which have both substituents again. So which one's better? Well, our first structure, the one on the left, we have 3 axial methyls, and we have 5 equatorial methyls. On the right, we have 5 axial methyls versus just 3 equatorial. So what's better? Well, we know the more equatorial, the better, especially if all of them are the same size. This one has 2 extra substituents in equatorial positions, and so this would be our most stable chair conformation.